So at this point, knowing that all we're doing is collecting the remainder instruction variants, for Example4DivRem, we're going to collect the remainder of the divisions and remainders. So we play the game as we usually do to hide the values that are going to be used from the compiler. And we're also going to play the size game by using long longs for some variables and an int for other variables, so we get the W variance. So compile this code and you get this assembly. 4 new assembly instructions: div, divw, rem, and remw. Div is the signed divide. Divide assuming that the operands are signed, and it divides the x-length rs1 divided by x-length rs2. So again, it could be 32, could be 64-bit. Treat them as signed, round towards 0 as usual, right? We just say how many times does rs2 go into rs1 evenly, not creating a floating point decimal version. So round it towards 0 and store the result into the destination register. So if we did a div on a signed negative 5534 in hexadecimal, or F's AACC, divide that by 6, and we get this all F's 1CD, so hex E33, negative E33. You can, of course, check this with your own calculator. Divide negative 9 by 3, and of course you should get negative 3. So on to divide word sized, which is again same thing, treat it as signed and use the word size of the register. So take the lower 32 bits of RS1 and treat that as signed. And you can see how this distinction of signed versus unsigned becomes important here, because when you truncate down the 64-bit register to only 32 bits, now it's going to be, is the signed bit of the most significant bit of the 32-bit value, is that set, and that determines whether or not it's being treated as a negative or positive number. So take the lower 32, treat it as signed, divide by the lower 32 of RS2, interpret it as signed. So, and going back to this example of negative 5534, or all F's AACC, divide by 6, we are now going to be using it as a word-sized value. So we're only taking the bottom 32 bits, but even as the bottom 32 bits, this is still negative 5534, and therefore, once again, the result will be 1CD with all F's in the upper bits. It would just be the 32-bit FFFFF 1CD, but we then subsequently do the sign extension up to the 64-bit value. Another example, divw, 5 divided by 6, my old stalwart, goes in there 0 times. Remainder as signed values, so treat the RS1 and RS2 as signed, do the modulo or remainder operation, and see what you come out with in the destination register. So now we're going to do that negative hex 5534 modulo 6, and we're going to get a remainder of negative 2. So this negative value divided by 6 gave us that negative all F's 1CD, but the remainder of that is negative 2. So all F's 1CD times 6 would give you negative 5532. So remainder of negative 2. All right, and 5 modulus 6, and a remainder of 5. Now remainder with word size, it's exactly what you would expect. Take the lower 32 bits of RS1, treat it as signed, and do the modulus operation on the lower 32 bits of RS2 and signed. And so again, because remainder is defined in terms of division, that's why the signedness matters here, because the net result of the division, you're going to take the remainder of whatever is left over from that. So going back to this example, all F's AAC, word size, so we grab the bottom 32 bits, but it doesn't matter because it's the same value in 32-bit as it is in 64. Modulus 6, and again, it is negative 2. 5 modulus 6 is 5, as always. I'm being very uncreative because I just wanted to get through these variants. I could have just went with one thing and not showed you the second one, but I gave you that bonus, completely unnecessary no-op of a remainder operation. Whatever. Anyways, look at the code, step through the assembly, and understand that you're just dealing with a couple new variants of the division and remainder that you already know and love. Variants for signed interpretation of variables and variants for word-sized signed interpretations.